Yes.
Okay, so let's move to the second and final part of the project status report, where we have overviews of new or upgraded experimental physics facilities, always from a control system perspective. So without any delay, we move to the first report, which is on the status of the laser megajoule facility. Our speaker, Hervé Courtet, is a controls engineer at the SEA Research Facility. He has worked for 19 years in the SEA Power Laser Department on the alignment of the megajoule laser and the production of laser megajoule facility optics. Since 2019, he is the head of the Laser Megajoule Control Laboratory. He will present to us the major evolutions of this facility since 2019, including new diagnostics and functionalities, and the results of the fusion milestone, which is a major milestone for the project. Hervé?
Yes, can you hear me?
Please turn on your microphone, share your screen.
Yes. Can you hear me?
Yes,
Yes,
we can
you
hear
have 12 minutes,
okay.
And 2 minutes prior you will be warned.
Okay.
Have a good presentation.
I'm sorry, I can't send my presentation.
Just share
okay.
the screen.
Okay, it's okay. Can you see it?
Yes.
Yes, but we see the presenters.
Yes, okay.
It's not in the presenter mode.
Can you put it in presentation mode, please?
But I'm doing it. It's okay?
We still see the other view, not the presenter's view. But maybe if you don't want to lose any time, we can.
Okay. I can see.
I think you have to open up first and then go into presentation.
It's okay or not? Can you see the presentation or not?
Yeah, we can see the presentation, but it's in editing mode.
It's in edit mode, yes.
Okay.
Not in presenter's mode.
Probably you go ahead.
Oh, I don't know. It's okay on my screen. Okay, so I will start. It's okay for you?
Yes, please do.
Okay. So, hello, my name is Hervé Courtet. I'm the head of the Command Control Laboratory of the Laser Megajoule facility. So, I'm going to give you an overview of the LMJ facility status. So, the Laser Megajoule facility is located in Le Barp, near Bordeaux, in France. The LMJ is developed by the Commissariat à l'énergie atomique et aux énergies alternatives, CA, and is designed to provide the experimental capabilities to study high energy density physics. The LMJ is a keystone of the simulation program. So this program combines improvement of physics models, high performance numerical simulation, and experimental validation in order to guarantee the safety and the reliability of the French nuclear weapon. So LMJ is constituted of 176 beams, 22 bundles of 8 beams, and one specific beam line for the petawatt laser petal.
Hervé,
so LMJ is
excuse me, Hervé, I don't see your slides moving.
Which slide you will see? The slide number 2?
It was stuck on the first slide.
Yeah. It's a problem. It's working on my screen.
It's fine. Just click on the slides.
Okay. You see which slide can you see?
Right now, nothing.
Nothing. Okay. I try it again. Can you see something?
No. Are you using double screen or something like this?
No. I did it.
I mean, I have a PDF of your slides. I could try that.
Okay.
Yes,
Can you?
Marcus, can you share?
All that.
I have opened it. Maybe I can share and just tell me
okay.
page up. Okay.
I have it already open.
Okay, thank you.
Can you see that?
Okay. Can you
Yes.
see now?
Yes.
It's
Okay.
big.
The second one? Yes, the second one. Okay. So I told you LMG is constituted of 176 beams, 22 bundles of 8 beams, and one specific beam line, the petal, petawatt laser. So LMG is a neodymium doped glass laser with an infrared wavelength of 1053 micrometer. The infrared frequency is converted in ultraviolet and focused by means of gratings on the center of the target chamber. LMG will deliver an energy of 1.4 megajoule during few nanoseconds and a maximum power of 400 terawatt of ultraviolet light on the target. Can you pass the next slide, please? Okay. So the beamline architecture is divided in 3 main sections. So the front end is made of 4 sources, 1 per laser hole and 88 preamplifier modules. Each preamplifier module delivers a 500 millijoule energy beam to the amplification section. So in the amplification section, the beams are grouped in bundle of 8 beams, and they are amplified to reach the energy of 15 kilojoule of infrared per beams. At the end of the amplification section, in each individual bundle is divided into 2 quads, which are directed to the upper and the lower hemisphere of the chamber by the means of transport mirror. The final optic assembly for frequency conversion and focusing is composed of 1 omega gratings, 2 KDP crystals to convert the infrared in ultraviolet, and 3 omega gratings to focus the beam on the target. So each beam is able to provide 7.5 kilojoule of ultraviolet on the target. So can you pass the next slide? You can see some picture of the equipment. So on this scheme, we describe the position and the status of the bundle in the different laser bay. So we have, at the end, we will have 22 bundles. So in this scheme, the green bundle are the operational bundle. In blue, the bundle being commissioned. And in red, the bundle assembled but not operational. In orange, the bundle are being assembled. So today, 9 bundles and the petawatt beam are fully operational. 1 bundle have been commissioned and will be fully operational at the end of 2021. And 4 more bundles should be assembled at the end of 2021. So the assembly of new bundles go on following a rhythm of 2 bundles per year. So can you pass the next, please? The next slide. Okay. So to insert the plasma diagnostics for the experiments, 4 systems for diagnostics insertion are available. So we call the system of diagnostic insertion SEED. We have 3 seed positions on the equatorial plane and 1 of the polar seed position above the target chamber. So you can see on the picture on the right the equatorial seed, and in the middle the polar seed above the target chamber. So 3 more equatorial seeds are coming, 1 at the end of 2021, another one in 2022, and the last one in 2023. So with appropriate handling equipment called BTDP for plasma diagnostic transfer box, we are able to move plasma diagnostic around the target following the needs of the experiments. So you have a picture on the left of the plasma diagnostic transfer box, and the same box on the right. You can see the BTDP with the polar seed, and we are transferring the plasma diagnostic from the BTDP to the polar seed. So can you pass the next slide, please? Thank you. So currently 14 diagnostics are operational and 4 more will be commissioned in the 2 next year. So it's offer a variety of imagers, spectrometers, scattering imagers, and complete pack neutron. So most of them are loaded in the system for diagnostic insertion. So you can see it with the cross pattern on the picture. But some diagnostics are present permanently as DP14 to measure the quantity of neutron. So regularly, 5 to 8 diagnostics are used during the physics experiments. Can you pass to the next one, please? Okay. So our strategy to preserve the optics of the final optics assembly is based on a complete chain, including acquisition, damage detection, damage growth block, and a recycle loop of the optics. So the main component for damage tracking is a vacuum window, which is an expensive component, and a safety component for it is a separation component for the vacuum and the chamber. So for now, the 3 first steps, acquisition, damage detection, and damage growth block are in use. And the first recycle of optics will be back on the installation around 2025. So the acquisition of damage is realized with our device called target chamber diagnostic module. So if you want more information about the target chamber diagnostic module, you can see the poster of Rome Enclos. So today we are able to generate spot blocker in a manual way for the moment, but we will be following evolution to generate automatically spot blocker in the beam based on the target chamber diagnostic module acquisition to prevent the damage growth. Can you pass the next one, please? Okay. So let's talk about PETAL. So thank you, Shenli, for the introduction about petawatt laser. So PETAL project is being performed by SIA under the financial auspices of the Région Nouvelle-Aquitaine, the French government, and the European Union. So PETAL is a very powerful laser, petawatt laser, which delivers the same energy as LNG beam, but over a period 1,000 times shorter. The first experiment with the laser PETAL happened in 2015 with a shot of 1 petawatt, so 1 kilojoule in 1 picosecond. So in 2016, we optimized the pulse compression to 570 femtoseconds. Between 2017 and 2018, we work on the quality of the focal spot by improving the phasing and the quality of the wavefront. And for 2 more campaigns in 2020, we adapt the facility to shot on a 25 micrometer wire with an elliptic focal spot. So the PETAL laser beam has very good result, and we are focused to improve the performance of the facility and the automatization of the process. So can you pass to next slide? The other one, if you. Okay. So since the last presentation of the LMG facility status at ICALEPCS 2019, a major milestone of the LMG project has been reached with the fusion milestone during the month of October 2019. It was the first experiment in cavity with 6 laser bundles. So by this way, we are able to provide more than 150 kilojoules on the targets. So the goal was to realize a thermonuclear fusion by implosion of deuterium capsule in a cavity and measure the neutron production by means of the plasma diagnostic 14. So the scheme on the right illustrates the 12 quadruplate illuminating the target with the rugby cavity, and in center you have the T2 capsule inside. So during this campaign, 10 experiments using 6 bundles have been completed. So next one. So the goal of the experiment is to test and qualify our simulation code. So you can compare the different image of the experiment with the 3D simulation. The image is very similar to the simulation, and the neutron yield is close to the prediction. So if you can send the short movie.
Oh, sorry.
On the right,
is
there is
PDF version.
It's a PDF. Yeah.
It's a
Oh, it's a
PDF.
PDF.
Sorry,
Okay.
I cannot.
So you could see the numerical simulation realized before the campaign, and it shows the implosion of the deuterium capsule inside the cavity in a lapse of time of 5 nanoseconds. Thank you for your attention.
Thank you very much, Hervé, for the nice presentation, despite the problems at the beginning. We are opening now the floor to the questions. Marcus?
Yes, well, sorry, I have to get sorted out here first. Sorry. Are there any questions? I think there's one in the chat. There's a question. Oops. Oh, sorry. Do you have a picture of LMJ control room? How many operators are normally there?
Oh, okay. I think I have picture, but not here. Moreover, it doesn't work very well. In the control room, I think we are 10 to 15 persons during the shot. And it depends of the number of diagnostics, the number of problem we have too. But between 10 and 20 and 15%.
Okay.
And we already have more rules because of the COVID too.
Mm-hmm. Thank you. I think in view of time, we have to, thank you, Hervé, for the presentation. I think we have to move on now. Thank you.
Thank you.
So our next speaker is Sergio Poppi from the INAF OAC in Cagliari in Italy. Sergio received a degree in astronomy from the University of Bologna in 1998 and joined the Osservatorio Astronomico di Cagliari in 2006, where he played an instrumental role in the setup and operation of the Italian radio telescopes. And in 2018, he became the head of operations. He is going to talk about the control system for the radio telescope called Discos Updates. Sergio, please.
Thank you very much. I try to share the screen. Okay. Can you show the presentation?
Yes, I can see the
okay.
presentation and can hear you.
So, hello everybody. Thank you for giving me the opportunity to show Discos updates. What is Discos? Discos is a common control software for the Sardinia radio telescope and the other Italian radio telescope. In 2004, we started the development for the SRT control software. At the time, we called Nuraghe. And the aim of this project was to provide the Sardinia radio telescope of a control software with enhanced performances. Also, we built a common infrastructure for the all the three Italian radio telescopes. In fact, in 2007, we started ESCS, that is Enhanced Single Dish Control System for Noto and Medicina. In 2015, we joined the development lines into Discos, which stands for Development of Italian Single Dish Control System. Discos is made of a common monolithic code base where has in charge, the common code base has in charge management, subsystems, bosses, user interfaces, libraries, and only the 23% of the code it is for differences among the telescopes, which are the Italian radio telescope. INAF is the National Institute for Astrophysics, manages 3 single-dish radio telescopes. One is the Sardinia Radio Telescope, which is located in Sardinia. The other one is the Medicina Radio Telescope in northern Italy near Bologna, and also the Noto Radio Telescope in Sicily. The observation can be run in both in single-dish mode or in networks for the very long baseline interferometer. In this mode, the Italian radio telescope are part of the EVON, the European VLBI network, the Italian VLBI, and also the East Asia to Italy near global VLBI. Well, let's look at the differences between the various telescope configuration. The SRT is a 64-meter telescope, while Medicina and Noto are 32-meter diameter telescope. They are fully all azimuthal, fully steerable radio telescope, but it can be seen starting from the antenna control unit that there are some differences. For example, the antenna control unit for SRT is based on backup PLC, while the other 2 telescopes are based on VXWorks, and all they have their vendor protocol. Also, for a focal primary focus and secondary focus optics positioners, we have even more different aspects. For example, we have different kind of links. For SRT, there is Ethernet, like in Medicina, but for Noto, we have serial. And also, for example, another difference is that SRT and Noto have active surface, while Medicina is not has not yet. It will be installed at the active surface only by the 2023. The difference even are also in the receivers, where there are other kind of links like GPIB and serial and other, and the protocols are different. So having a common control software is a big challenge to deal with. This how we manage these differences. We're exporting first the framework on which DISCOS is based. DISCOS is based on the ACS, the ALMA common software, which has a distributed object architecture where the basic unit is a component, and a component exposes interface to the other components. Moreover, ACS gives us the ACS framework gives us many services like a configuration database, error system managing, logging system, a time system, and other services like alarm system, for example. Also, we designed in subsystems that in the ACS framework are containers. There is once there is a supervisor and many subsystems like front ends, optics, the antenna pointing, many services, also active surface. And each subsystem is organized in 3 layers where there is on the top, there is the user layer and telescope layer where there are the different models, and also a service layer, the bottom one. On the top, there is also the user interface. We have where the user, that are the observers, for example, give command through the operator input and check the status on each text-based window. For example, mount, antenna boss, so on. Well, I start with the updates that I'm going to show you. One of the first big update on our control software is related to testing, to test-driven development. We are adopting test-driven development where with the unit cycle of unit tests, followed by integration test, functional test, and finally acceptance test. It's important that the integration test and the function and the acceptance test must be done with the real hardware, with the real telescope. But sometimes it's not possible. So it would be important to have a simulator behaving like the real world. In this way, we built a simulation framework. Simulation framework is made of basically two layers: a networking layer and a simulation layer. The networking layer has in charge to get the command, to handle them, to send to the simulation layer, which parse, update the status, simulate the execution, the reply, and back to the networking layer. After that, the client receives the reply, the response from the simulation. I want to focus on a very important feature of the simulation framework. We can handle all the subsystems. We can simulate all the subsystems. In this way, we can perform dry run of discos and performing testing on functional tests without asking for telescope time. Telescope time is very important. It's a very important resource that must be given to observations. So in this way, having a simulation framework, we can speed up testing, bug tracing, bug fixing, and without the need of the telescope. Another upgrade is related to, it is called surrogate, and it is a layer which abstracts from the operating system. Well, the ACS framework is linked with a very strict operating system. With the surrogate, we can put in this layer, we can make an abstraction where there is a sampler that samples the ACS properties, the discus properties, send them to the Redis database. Redis, it is an on-memory database, and after that, they are stored in a persistent database. Information and comments.
2 more minutes.
Oh, okay. Can send to the Redis DB or the HTTP server, like for example, we did a Grafana client to handle the communication, to check the pointing. Another important thing is the automatic deployment. Automatic deployment allows us to have environment, production environment, and development environment aligned. In this way, we can speed up development, and we are sure to to keep everything aligned. Automatic deployment is made with Ansible. A new integration, a new feature is that we got new funds to upgrade our receivers for the SRT and the other radio telescope. The project is expected to complete it by July 2022. So we are integrating our control software all the receivers. This will allow to give us new performances, new operativity up to 116 gigahertz. So summarizing, I summarized the updates, which are test-driven development supported by the full hardware simulation, an automatic deployment for production and development, and also this middleware, Surricate, to abstract from the operating system. And also, finally, the integration of the new receivers, which will give us a new opportunity, new operativity for our telescopes. And with this, I thank you for the attention, and I give you some links where we're going further, going through our work. Thank you very much.
Thank you very much, Sergio, for this interesting overview of your developments. Are there any questions?
I see no questions on Zoom or on WOVA. Anyone putting hands up? No?
I have a quick question, Sergio. Do you develop this centrally? So are you all located at one point?
No, we are in.
Or are you distributed?
We are distributed just partly in Sardinia, partly near Bologna, and also in we in 3-4 places. Okay. Also in Milan, in Brera, and in Sicily, in Noto and Catania. So starting from the beginning, not only related to our situation, but we have been always spread among the Italy.
Mm-hmm. Okay. So yeah, thanks very much again, Sergio, for this talk and this overview. And we should, I think, continue with the next speaker.
Okay, so we move now to the next report on the status of the CERN cryogenic controls for today and the outlook for tomorrow. Our speaker is Marco Pesetti, who is a process controls engineer in the cryogenics group of CERN, and he is responsible for the controls and electrical support. He will present the LHC cryogenics controls architecture, which started in 2000. Since then, the control system has seen quite a lot of evolution in order to increase the safety and to improve the performance based on their experience. And the final part of the talk will present the evolution of the control system towards a new service-oriented architecture. Marco?
Yes.
Please share your screen.
Thank you, Eugenia, for the introduction. Can you see the slide?
Very well.
Okay, perfect. Thank you. The outline of the talk will be as follows. Let me introduce CERN, as it's based between the mountain of Jura Mountain and Geneva Lake. We have the LHC that is seated at 100 meters underground, and its circumference is 27 kilometers. The CERN infrastructure is represented by 50 cryoplants, and which are big, medium, and small, and 4 large calorimeters. And the control system for the cryogenic infrastructure is shared with a synergy with another group that this is working very well. Let me introduce you the result that we have after 20 years of the availability, because the CERN management asked us, the cryogenic group, for the 97% for the LHC, for the cryogenic availability. This means that for each CRAL plant, we need to be more than 99% available, and the control system has to be also available 99%. We are struggling every day with availability optimization effort. And this is continuing to be because we have a running physical running campaign that it goes beyond now, starting with the run 3 and going beyond 2030. The present cryogenic control system implementation is this is the common ecosystem that we have at CERN. Is based on the 4 lower layer of the classical 5-layer control system architecture. We have the instrumentation layer. We have the control layer where the process duty are executed. We have the supervision layer that is running with industrial WinCC OI SCADA. And we have the maintenance layer where we do also, especially some functionality, especially like the accelerator fault tracker, and everybody is connected to the general purpose network, while the PLC and the control unit are in the technical network for security reason, of course. But I wanted to just highlight 2 main aspects for the success of this control system. One is the idea of the framework, Unicus framework, is to put the ease of the operation ability to follow the evolution of the process and understand all the dynamics of the process, including the fault, in order to react. And this has been very important in the commissioning phase, but also in the running campaign phase, where we can identify the fault appearing. The second point is very important, is the well-structured application generation process that has opened the door to the very important continuous integration technologies that now we able to perform a generation of our control system, update and optimization every single time we need, with very high quality. For the near future solution that we have given to the for the run 3, we have focused our effort in order to procure to the information needed for the operation within the SCADA system. And with one click, the operator is able to collect and find easily for each instrument actuator the electrical schema, the maintenance-oriented database asset management, where all the information of the instrumentation actuator are saved, and connect to the smart logbook, where the operator can create work orders for the preventive maintenance or corrective maintenance. And for the second part, where we are seeing that in the high energy physics facilities, the radiation will be a major problem for our control system. And we are thinking about our solution, bringing literally walls underground. And we are also investing a major project with the radiation tolerant electronic solution. We will see later on why. But let me introduce the tomorrow vision that for us, the future cryogenic control system must be based on cyber physical control system cloud, integrating the service-oriented architecture and Internet of Things. The service-oriented architecture replace, as we have the hierarchical communication existing in the classical ESA layer, with a flat exchange of information, which is adapted to the need of various components communicating each other. And so the device will communicate between them, creating this framework of communication. And for this, the IoT, internal device specificity, is placed in our solution, the future solution, with this device that are node together with several interaction services across the level. And there will be no place like now in the lower level of the control pyramid with, for example, the plug and play functionality, which let the device integrate the network in self configuration and discover all the functionality by itself is a great feature that we would like to exploit, also with the other specificities that we have. But one thing is Internet of Things introduce new security challenges for network and security team. We have to be careful about this in the future. For this challenge, we should look very carefully at the framework that implement the complex knowledge on creating a control system. The free axis that we can see in the RAMI method in the reference architectural model industry is the one that we're looking for. For example, in the first axis, the factory is already there. We are using these ideas while we are constructing our control system. Product life cycle also, but we should also take advantage of this framework. And the third axis, the architecture, while the composition of machine into its property, structured like layer by layer, like the asset integration, communication information, and this is need to be worked on. So the CERN should develop an open source using all these evolution with the hardware, using all this concept. And specifically for high energy physics facility, radiation environment is something that we cannot take into account. And of course, if you want to have financing, we need to reduce the cost. And one simple, obvious solution will be to reduce the cabling cost. And we will see how we would like to proceed. For the time being, we have coupled the two controllers, one the PLC, which are very good reliability, and the other the front-end computer running the CERN FESA framework, which come to solve all the complex logic that we need, like the calibration curve for instrumentation. And now for the future, we should combine all the good things that has the PLC and the FEC and find a new controller running compatible with this SOA and IoT. And for this, of course, we have to look to find a way and to structure and to monitor the communication. And this will be, of course, relying on the OPC UA and with those capability to integrate the IoT functionality. And of course, for the communication with process component submitted to radiation, of course, we design our facility with the alcoves that protect our electronics, but we need to increase the radiation tolerance of our electronics because the factor that the simulation are expecting is 500, between a factor of 500 and 200 for the stochastic and cumulative expected effect. So this could be a very good initiative that CERN has taken, is the DOT modular platform that has a solution for radiation and non-radiation area, and it can be represent a common platform for the design of a dedicated electronic card, or not, of course. And this is we believe really neat, and we are starting working with Xavier for doing this. And of course, for the reducing cabling cost on our facility, the proposal based on 60 gigahertz wireless must be followed. There are some initiatives at CERN outside, and we really need to be careful to watch for this solution, for the wireless communication and cable or wireless powering, because the power wireless is not yet the solution. And for conclude, we have seen that for the last 20 years, the cryogenic control system has been successfully implemented. Now, for the future, we need a rupture that the CPSC control paradigm we can bring it to us, but we need to rethink completely the development process. And we have some challenges that they require the federated effort to include the technology breakthrough without missing the rupture that may happen, profit of the past experience, use the faster pace progress observed in industry elsewhere, and we need to create conditions for trustful and win-win collaboration for our partners. One point is find the right balance between open source solution based on open standard of the shell component without hesitation, and the laboratory, CERN or others, shall keep the strategical domain and avoid as much as possible vendor lock-in issues. The key is synergy between the control team. And I'm finished.
Thank you, Marco, very much.
Thank you very much for the nice talk.
Yeah.
We open to the questions, Marcus?
Yeah, we have questions. There is one. Which security features are you planning to add?
This is not my domain, but at CERN we divided drastically the Ethernet technical network, the GPN, by some exposed machine. So this is a service that we have. I was just underlining the fact that if we bring some IoT device that need outside information that come from the ecosystem of CERN, we need to find a way to let them communicate in order not to limit ourselves and to find the right balance as we are doing now.
Okay. There's another question. How do you translate the RAMI availability for the whole cryo plant to target reliability of individual INC components?
Because in the RAMI, we think as a whole. Now we are just having a logbook and MTBF thing, and we are just historically having a critically of the sensor that or the actuator that fails or any part, critical part. We need to think at the beginning using the RAMI availability, but this is something to be worked on.
Okay, thank you. I think we have to move on. There's another question. Yves-Marie, you probably have to address this directly to Marco. Thank you very much again, Marco, for this nice presentation and overview.
Marco.
Thank you.
So our next talk is, I will stay with the CERN, Polynikis Tsanis from the NTUA in Athens in Greece. He's working at CERN as a postdoc student, and he is involved in the ATLAS experiment and heavily working on the new small wheel detector upgrade project. The title of his talk is The Control System of the New Small Wheel Electronics for the ATLAS Experiment. Polynikis, please share your screen.
Yes, thank you very much. So, can you see my screen?
Yes.
Okay, perfect. So I'm continuing. So I am Polynikis Tsanis, and I will present you on behalf of the Atlas Mune collaboration, the control system of the new small wheel electronics for the ATLAS experiment. So this is the outline of my presentation, but I will go directly to the presentation. So regards the new small wheel upgrade will replace the current small wheel of the Atlas Mune spectrometer to handle larger particle rates. It's important for round 3 and vital for high luminosity LHC after 2028. So this is a cartoon of the ATLAS experiment, and here is the region where the small wheel is placed, and now currently this has been replaced by the new small wheel. For the new small wheel, this will provide high precision muon track reconstruction and tracking information to the atlas at high rates, and thus eliminating the issues of the previous small wheel. It consists of 16 sectors for each new small wheel, and each sector has 16 layers. And as for the new small wheel detectors, it consists of the micromegas, a gaseous detector, mainly for precision tracking and also for trigger, and another gas detector, the small thin gap chamber, STGC, mainly for trigger, but also for precision tracking. So regards the electronics of the new small wheel, in total, the new small wheel is a fully redundant trigger and tracking detector system, and it is supported by advanced electronic scheme and ready to handle the challenge of increased instantaneous luminosity of the high luminosity LHC. And for the question if the new small wheel electronic system is really small, it's just some bullets like it has separate configuration monitor, readout, and trigger path. It has over 2.4 million readout channels. It has a total of 7.5 thousand electronics board, a number of 60,000 ASICs, and for monitoring, the parameters are over 100,000, and for configuration, we have 1 million registers. So here is a schematic of the electronics overview, and just an introduction. We have different areas, like we have the front end boards. In the middle, we have the on detector on chamber boards, and in the end, we have the service area, which all the service and the backends are located. And all this communication is going through the GPT and the CA. And the e-links are used for level 1 accept data and data monitoring, basic clock and TTC signals, configuration of the ASICs, monitoring temperatures and voltages, and the FPGA configuration. Regards the architecture, it lies on newly introduced readout scheme of Atlas, and it has mainly three hardware components. The first one is the Felix, which is the optical link aggregator system, the TTC distributor, and the BZ, which in fact is a server PC which hosts two BNL 712 PC cards. It has another one system, the data handler server or software rod system, which is a software-based readout driver, and then the TTC system. And in this new small wheel electronics architecture, is the first time that the DCS, the calibration, and the configuration share the common path to the detector electronics through the GPT SCA, and for this we use the SCA OPC UA server. So for the GPT SCA chip, it's a gigabit transceiver slow control adapter, and it's part of the GPT chipset, which purpose is to distribute control and monitoring signals to the front-end electronics embedded in the detectors. So it has this chip is really useful because it provides several user interface ports like SPI, I2C, JTAG, digital to analog converters, GPIOs, and of course for monitoring ADC 12-bit ADC to analog to digital converters. So how it looks in the end? So for the whole communication, we rely on the Felix and the OPC and the SCA OPC UA server. So we have three regions. We have the on-off detector electronics, which you can see we have the electronics equipped with the SCA. Then we have the Felix machine, which inside of it is running the SCA OPC UA server. And then in the end, we have the various backends like the DCS for monitoring, the DAC for configuration, and the calibration backend. So the first step is that first we prepare the Felix by configuring the E-Link ports, and then via initializing the SCA OPC UA server, we establish the communication between the SCAs and the Felix. And then, of course, all these devices are accessible through the network and through the OPC UA server. And in the end, through the DCS backend, we can monitor the various temperature and voltage levels of the electronics. We can configure the various electronics, and we can calibrate the electronics via the common SCA OPC UA server. So the final system setup, it consists of 28 Felix servers, and there we'll have 32 OPC servers, and for each sector we'll have one server, and through the network we'll communicate through all of them from the backends. And I will do now an introduction to the Atlas detector control system. The Atlas DCS has the task to permit coherent and safe operation of Atlas and to serve as a homogeneous interface to all sub-detectors and the technical infrastructure of the experiment. The DCS must bring the detector into any desired operational state, continuously monitor and archive the operational parameters, signal any abnormal behavior. The Atlas DCS is developed via the WinCC SCADA system, and it has a lot of characteristics and features like flexibility, hardware connectivity. It can provide several connection protocols, and it's a really easy system in order to create distributed systems. And here is an overview of the current status of the Atlas detector control. So regards the NewSmall Wheel detector control scheme, due to its complexity and long-term operation, the NewSmall Wheel requires the development of a sophisticated DCS. And this system is necessary to allow the detector to function consistently and safely, as well as to function as simplest interface to all the sub-detectors. And the plan is to integrate within the Atlas and the Neon part, the two new sub-detectors, the Micromegas and the STGC. And already the NewSmall Wheel DCS architecture and its integration has been finalized. And some of the projects that concerns the high voltage, low voltage, the electronics that we are talking today, the MDM, which relates to B field or T sensors, temperature sensor, and several other infrastructure regards to the detectors, detector operation like cooling and gas. So as for the electronics control system, for the electronic self-operation, an advanced control system within the Atlas DCS is required in order to monitor the electronics using the SH chip, which is installed on the 8,000 front-end boards of the NewSmall Wheel. And it features 6.4 thousand GBT-SCA. It runs over the common SAO-PCUA server, and it monitors in parallel 100,000 parameters. These parameters consist of power temperature sensors, on-chip temperature information, diagnostics information, and alarm handling of on each parameter. Of course, we are following the Neon's existing look and command architecture. Its logic is based on the hierarchy of finite state machine, and it facilitates the shifter expert operations. And as you can see through the various images, for each individual layer, a main panel has been developed and providing the user with useful information reflecting the state and the status of the detector and the electronics. So also, as I said, it's the first time that we have the configuration, the calibration of the DCS on the same path, on the same SAO-PCUA path. And there we had the case that on all the front-end boards equipped with the readout ASIC chip called VMM, the SCA analog input is common for the VMM calibration and the temperature monitor. Thus, during calibration, VMM shows fake temperature values, so a plugin between the DCS and the DAC should be implemented. So the solution found via the common OPCUA server, where the responsible team developed the free variable concept, which is an OPCUA item which can be controlled and monitored in parallel with both the two clients, the DCS and the DAC. So during the calibration run of the Atlas, the DCS will monitor the configuration status for this specific VMM of the FEB, and the alarm will be disabled for the corresponding FEB's VMM. And more DAC and DCS interactions, like through this system, we can monitor the Felix status, the GPT link health status, and of course, communication between the DAC and the DCS for the low voltage status of the electronics. And this is the summary of my talk. The NewSmall Wheel is a fully redundant trigger and tracking detector system supported by an advanced electronic scheme and ready to handle the challenges of increased instantaneous luminosity. Due to its complex and long-term operation, the NewSmall Wheel requires the development of a sophisticated DCS. The new small wheel electronic system is really challenging due to the massive number of boards and also, of course, custom-made boards and ASICs and FPGAs. Another challenge is the dependence of the new small wheel electronics on the new technologies based on the Felix and the GBT-SCA. And of course, the first case that we use the common SCA OPC UA server path for several backend applications. So right now, the system setup architecture and operation has been finalized. The low-level segments of the project has been fully deployed with the main components being fully functional, and currently the control system is under implementation phase for the Atlas Calmer. So yes, thank you very much for your attention.
Thank you very much, Paulinakis, for this nice overview.
So we open it for questions. There is no questions on Zoom. I'm checking now on Wova. I don't see any questions on Wova. But I have a question myself, if I am allowed.
Yes, of course.
The implementation of the electronic system, which should be prior to the implementation of the control system, has it occurred any delay due to COVID and the situation that was for procurement, for installation, for integration, or everything went as planned?
Yes. So yes, nice question. So the thing is that this project, or the plan of this project for the electronics is to be ready before COVID, and for thanks God we got in our hands all the related electronics and the chips. So the left that the part that was missing and done after the COVID was the commissioning and the installation of these electronics into the detectors. So we were really lucky, and we didn't affect of this lack of electronics due to COVID.
So the implementation of the control system is progressing as expected?
Yes.
No
Yes.
delay.
Now,
okay.
Exactly.
Okay, then thanks again, Paulinakis,
Thank you very much
for this overview, and we will proceed with the next talk.
Okay, so this is the last presentation of our track, which is a report on the control, monitoring, and safety mechanisms of the electronics for the MACE telescope camera. This camera is one of the most important subsystems of the MACE telescope. Our speaker, Surab Kumar Nima, is the scientific officer in the BARC Research Center, and he will present the overall architecture of the camera control mechanism with a focus on software and hardware challenges. Surab? Can you please unmute yourself, share your screen?
Yeah, thank you very much. Yeah, just sharing the screen. So is the screen visible?
Yes.
Yeah. So thank you very much.
Please go ahead.
Good afternoon to all of you. Myself, Saurabh Nima from Electronics Division, BARC. I'll be presenting the talk on MACE camera electronics, control, monitoring, and safety mechanisms. First of all, I would like to thank the organizers for giving me the opportunity to present this work in front of such a scholarly audience from all over the globe. The MACE telescope has been installed in Leh, Ladakh, India, at an altitude of 4,270 meters above sea level. And this telescope has a 20-meter dia reflector dish. And at the focal plane of this reflector dish, there is a camera electronics, which is the focus of today's discussion. So if we go directly towards this camera electronics, so this is a front view of the camera electronics, where we can see 1088 photomultiplier tubes mounted. These photomultiplier tubes are grouped into an array of 4x4 pixels, and this electronics control and DAQ electronics for this array of 4x4 is implemented into a module called camera integrated module. So there are such 68 modules which are controlling this camera electronics, front end of camera electronics. The USP of this camera design is that all the electronics for PMT bias generation, analog signal processing, trigger generation, data acquisition, digitization, and data acquisition has been implemented in this 2 meter by 2 meter camera electronics. Only power supply and communication cables are coming from ground station to this camera. If you see the rear view of this camera electronics, we can see the cooling fans of all the 68 camera integrated modules, and there are back-end units, which is this one is second level trigger generator, and this one is data concentrator. It collects data from all the 68 modules. Then there is a central camera controller, which is responsible for overall control and monitoring of this camera electronics. It gets commands from ground station and controls the camera electronics accordingly. If you see the overall control mechanism of this MES telescope, so it can be controlled locally from control room at Hanle, which is a site, or it can be controlled remotely from remote operator console at BARC Mumbai through a proprietary link. And there are data archival servers which store the event data. The most important and complex part of this camera design is front-end module. This front-end module houses electronics for 16 pixels from signal conditioning to pulse shaping and first level trigger generation, as well as high-speed sampling, digitization, and packet building. Overall control of this front-end module is the responsibility of local controller, which is implemented in a microcontroller. It gets commands from central camera controller. Now, this is the photograph of that front-end module, which is called as camera integrated module. Just I will briefly describe the event flow. So the central camera controller through Ethernet gets configuration commands from operator console and accordingly initializes all the subsystems of camera electronics. And this is an event-driven system. So the system camera waits for onset of events of actual interest, which is a Cherenkov event. As soon as there is event, the second level trigger generator detects time-space coincidence in the nearby pixels and generates a master trigger. This master trigger is given to all the camera integrated module. All this camera integrated module, after receiving this master trigger, generate the event data packets and send independently through point-to-point link to data concentrator. Data concentrator builds up this event data packet, adds timestamp, and also checks for event data synchronization across all the SIMs, and then transfer this data to data archival servers over 1 Gbps Ethernet link. Now, control and monitoring functions, which are the main control and monitoring functions which have been which are the requirement based on which we have implemented this system, is sequential powering of camera just to avoid any power current surges. Then after powering, each module is subjected to power on self-test and various communication links are also tested. Initialization is the requirement of various subsystems. Then we need to do a regular monitoring of critical experimental parameters. Then ensure synchronization of event data. I'll explain this thing. Then PMT light overexposure protection and various system safety and fault diagnostics. So this is the architecture block diagram of MES camera control system. This camera control system is mainly designed around central camera controller module, which I have shown earlier. So this camera controller, central camera controller, is designed to be working in extreme environmental conditions, and it has been tested for those conditions. The various subsystems of this CCC, central camera controller, microcontroller card, PC104 based plus base SDTC and FPGA sections. So in order to cater to the requirements, sequential powering of camera, RS485 link is used for sequentially powering of the camera integrated modules. And then POST communication link test, POST and communication link tests are carried out through I2C link, as well as SPI link for SLTG and data concentrator, SLTGs, trigger generator and data concentrator. Then through this I2C and SPI links, initialization of various subsystems is carried out, and regular monitoring of critical experimental parameters is also carried out through these links. I2C links is working at 100 kilohertz rate and SPI is working at 1 megahertz rate, clock rate. We ensure synchronization of event data through this, which is algorithm is implemented in data concentrator. I'll explain this in detail. And then PMT light overexposure protection algorithms are implemented and they run concurrently in all the camera integrated modules for each of the pixels. Then various system safety and fault diagnostic features have been implemented. In addition to this, there are temperature sensor and fence interface units installed in camera electronics, and central camera controller is also responsible for safe operations of camera shutters as well as LED calibration units. So various experimental parameters are regularly monitored, like high voltage anode current discrimination threshold, and this gives the confidence that to ensure that safe and stable operating parameters are there throughout the observation, and they are displayed during the observation on the operator console, as well as all these data are recorded in archival system. During analysis, physicists analyze these parameters and gets the confidence about the event data quality, that there was no interference during the observation, external interference. So one of the safety diagnostic feature I'll explain right now is POST check. We record all the POST status of all the modules. And just one example is there. In one of the camera integrated module, one board was not giving a proper version information. So the system on its own, central camera controller disables that module for that particular observation and continues with the observation with all other available active modules. Then during observation, when we are observing a gamma ray source in the near vicinity, if there are bright stars, so they create a lot of light on few of the nearby pixels, thereby generating a lot of spurious trigger of for the system. So to avoid those scenarios, local microcontroller and bright star masking algorithm has been implemented. This algorithm checks
2 minutes left.
Okay, thank you. So this algorithm checks for scalar values for all the pixels concurrently and disables a particular pixel if the SCR value crosses a threshold value of 1 megahertz, which is a configurable parameter. This and when it comes to a 70% of set threshold, this pixel again takes part in trigger generation. Similarly, PMT light overprotection algorithm has been implemented in local microcontroller, which checks for, let's say for this example is for anode currents. So this checks for anode current threshold value. For this example, it is a 5 microampere. If it goes beyond that, it switches off the HV supply to that PMT so that the productive life of this PMT can be saved. So once this light interference source goes away, it continues the experiment after this thing. Then there is a recovery of event synchronization loss. So DC continuously data concentrator checks for event synchronization If there is no loss of synchronization, it continues. If there is loss of synchronization due to any extreme environmental conditions, the central camera controller on its own recovers this situation within a time of 3 seconds and without any intervention of operator. So the conclusion, MES telescope is operational since early 2021. Control and monitoring features of camera electronics have been thoroughly tested and working satisfactorily as per design specification. Event synchronization loss is observed very rarely, only during extreme environmental condition of like -20, -30 degree ambient temperatures. PMT light exposure protection algorithms has been working satisfactorily. We have seen few vehicular movements around sometimes, but that light falling on camera, immediately this exposure protection algorithms start working, and the PMTs are safe every time. And bright star algorithm has been found to be working satisfactorily with proper selection of bright star masking thresholds. The contribution of events due to this bright star pixels has been reduced from 8% to 2 to 3%. Thank you very much for your attention.
Thank you very much, Sura, for the very interesting talk. I can see there is one question, but I wonder, since we are 5 minutes late and the other session has already been started, if we should go to the questions now.
I think there's time for one question because we started late. Yeah, Gubal is asking, from your slide 4, it seems your remote control is through wireless. You have the satellite uplink. Any concern on its reliability, or your system can tolerate missing control over short periods, like a few seconds?
Yeah, it has been tested to be working reliably. And it's a proprietary link, not sharing any internet. So it's a dedicated link and its throughput is ensured. So we have not seen any lag as such, and it works reliably.
Okay. And maybe there's another question on WOA that's probably a short question. What is the source of the master trigger?
The source master trigger is generated from second level trigger generator. The second level trigger generator gets the information of first level trigger generator from this camera integrated module. There is a threshold value set for each of the pixel. If the pixels are crossing those threshold values, this first level trigger information is sent to the second level trigger generator, which checks for the coincidence within a short period of 8 to 10 nanoseconds and checks for 4 nearby neighbor pixel hits in a short period of 10 nanoseconds. So this is the coincidence check, time space coincidence check.
Thank you very much. Yes, with this, I think there are no further questions. Thank you very much again, Saru.
Yeah.
So
we're closing the session. And thank all the speakers again for your contribution.
And the attendees for the very interesting questions as well.
Yes.
Thank you very much.
So,
thank you.
Thank you. And with this, we close the session.